So your theme of the FDP is e-mobility, right, Simon?
Yes, sir.
Excellent. So Dr. Minal, your expertise also belongs to power electronics?
Sir, actually control application of power electronics, sir. Not purely, but
Okay.
what we are doing some different topologies and control I can apply there.
So you did your PhD from which place?
Sir, NIT Durgapur
NIT Durgapur, okay.
under Subroto Banerjee.
Uh-huh. So you joined NIT Jamshedpur in which year?
Sir, 22.
Okay.
Earlier I was in Manipur.
NIT Manipur.
Yes, sir. From 15 to 22 I was in Manipur.
Okay. Okay. So just let me know if I have to start the things, right?
Okay, sir.
Give
5 minutes, I think. 5 minutes.
Sir, we'll wait till 6:05.
Ha,
Then,
okay. So I'm around. Just let me know, right? Just ping me up, right?
yes, sir.
Okay,
Yes, sir.
okay,
Yes.
definitely. अरे आज क्या हो गया 35 ही हुआ अभी तक
Sir, we'll start. Those are coming, they'll join.
Okay, so should we
Sir,
start?
I'll introduce then. Uh, a very good evening to one and all. Welcome to day 3, fifth technical session of 6-stage online faculty development program on recent advancement in e-mobility for developing power utility, sponsored by AICTE ATAL. Our today's technical session expert is my guru, Professor Rajeev Kumar Singh, sir. On behalf of the organizing team, I welcome you, sir, in our today's technical session. Before you start your expert lecture, sir, I would like to share a short biography of you with our participants. Professor Rajeev Kumar Singh is an accomplished professional in the field of electrical engineering. He earned his BTech degree in electrical engineering from the College of Technology, Pantnagar, India in 2001. Following that, he pursued his MTech degree in electrical machine and drives from IIT BHU Varanasi, India in 2003, and in 2013 he completed his PhD degree in electrical engineering from IIT Kanpur. Currently, Professor Singh holds the position of professor along with head of the department in the Department of Electrical Engineering at IIT BHU Varanasi. His research interest primarily focus on renewable power conversion for hybrid microgrids, power conversion for electric vehicle, hybrid electric vehicles, optimal charging, discharging of energy storage systems, and converter modeling and control. Professor Singh's contributions to his research field are evident through his extensive publications. He has authored around 50 transaction journals papers, one magazine, and around 91 IEEE conference papers. Additionally, he has written few book chapters and holds 2 patents. His expertise extends to project management as well. Professor Singh has successfully completed 6 sponsored projects, while an additional 6 projects are currently going on with him. He is actively involved in developing next generation low cost onboard technology to enhance the charging infrastructure for electric vehicle in our country. Recognized for his dedication and achievement, Professor Singh was honored with the Syama Bharsani Benko 64 Best Educator Award by IIT BHU Varanasi in 2021. He also served as Associate Editor IEEE Transaction in on Industrial Electronics and Guest Editor in MDPI Energies. Professor Singh holds the position of Coordinator for the Power Thrust Area within the IDBT Hub Foundation at IIT BHU Varanasi. As the coordinator, Professor Singh is responsible for overseeing and managing activities related to the power thrust area, which focus on research, development, and innovation in the field of power transmission. Professor Singh is leading a significant project that involves collaboration between the US National Science Foundation and the Technology Innovation Hub supported by India's Department of Science and Technology. Throughout his career, Professor Singh has received notable accolades, include the Best Oral Presentation Award during the technical session Digital Control of Power Electronics 2 at the IEEE ICON 2012 conference, which held in Montreal, Canada from October 25 to 28, 2012. He is also serving as the Secretary IEEE UP Section 2024 and the Chairman of the IEEE Industrial Application Society Chapter at IIT BHU Varanasi from 2021. With this, I would request my guru, Professor Rajeev Kumar Singh sir, to kindly enlighten us with his words of wisdom. Sir, please.
Thank you, Simant. Thanks for this comprehensive and long introduction. I have no words to describe all these things. Yeah, but good to see you. Good to see Dr. Minal Kanpi Sarkar. And the topic essentially that you guys have selected to conduct this workshop is very relevant, right? All across the world, people are talking about electric vehicle and in larger perspective, in fact, on electrical mobility. So if you say electric mobility, it does not confine only within the framework of electric vehicle. Lot many other things are also they get involved into it. So I will share my screen and try to, the way I have actually tried to uh, maneuver my today's talk. So I will try to touch upon two aspects. So is my slide visible?
Yes, sir.
Yes, sir. Yes, sir.
So everything is okay, all set, right? Am I audible and slide is visible,
Yes,
right?
sir. Yes,
Yes, sir.
Yeah.
Yes.
So, very carefully, I thought of selecting this topic that basically, if you look at the title itself, it has got eventually two components. One basically says that what is smart grid ecosystem, and not only smart grid ecosystem, how do you make cyber resilient, right? Because the concept of a smart grid includes cyber physical network connection, and when you connect your smart grid with the cyber physical network, actually you need to also look into the cyber resiliency part of it. And then, in order to align my talk with the theme of your FDP, so what I thought of that, okay, if there is a smart grid ecosystem, of course, cyber resiliency is involved into that, then how the electric vehicle basically is going to create an impact onto that. So, of course, if you talk about electric vehicle, charging would be there, standards and other protocols are there. So the entire, this session would be segregated into two different parts. One would be revolving around the cyber resilient smart grid ecosystem, its requirement, what do we mean by this, what are the roles of power electronics and other control aspects into it. And then, of course, yes, e-mobility has really impacted a lot all across the world. Because if you talk about the sustainable, development, sustainable tech development, greenhouse emission, you have to talk about the electric vehicle. And the power of electric vehicle has gone up like, if you say that you know something about electric vehicle or you do something related to e-mobility, people accept you as a very knowledgeable person. So that has become the power of electric vehicle or e-mobility is like that. So just moving on, let us try to understand, and I request participants basically you can interject me in between also. Let's have make it an interactive session. You can unmute yourself and keep interacting with me in between also, or if there is an issue with your voice, you can post your question on the chat box also. I'll keep regularly looking at the chat box and then try to answer your apprehensions. So what do we mean by how we conceive or interpret the conventional power grid architecture? So if you look at conventional architecture, somewhat looks like this. So you generate power from using coal or nuclear or oil. These are the resources with which the power is basically generated. Then you install a step up transformer, you transmit it through the transmission grid. Subsequently you transmit that power to a substation with their a distribution step down transformer used to be there, and with the help of that step down power you supply different users. Users may be residential, the commercial or industrial users, right? So entire ecosystem is unidirectional. So eventually, if you look at the entire power flow architecture, basically in the conventional power grid framework, so you will find that okay, you are generating power, transmitting it, again feeding it to some distribution station, and then making it useful for your your loads, either residential, commercial, or industrial purpose. So there is a unidirectional flow of power, right? So that basically earlier that was okay, but with the development and with the evolution of the technology and with the evolution of the demand that we have nowadays, that basically kind of has has given a thought to the technocrat that okay, this basically is the architecture that is not the architecture of a future. So the challenges that have been identified in this one is, as I said, that it is unidirectional in nature, and there is less communication network involved in it. You will not find any communication basically happening between the load and the source and the source and the other source, etc., etc. So essentially it is kind of one-way channel. You are producing, transmitting, distributing, using it. So no further information. There is no intelligentsia involved into it or smartness involved into it. And not only that, this is more prone to failure and blackout. In my early days when I used to be the kid basically. So even now also, there are many places in the country that basically get hit with this power shedding and all. And not only power shedding, you might have been observing quite often that during summer period, in the peak period, transformer is blowing up. There is a failure in a distribution transformer. All those things are happening. So this is another challenge basically, that with the time that have been observed in the conventional power grid architecture, and everything is manually monitored. There is no automated operation onto that, and no smartness into that okay, by having the remote by placing yourself or having at the remote location, you cannot get the idea of what is happening. You need to go to the place, to the installed location, and then get it done. So these are the things that are the issues related to the manual monitoring. Then efficiency, of course, yes, right from the generation to the use, the efficiency is not as attractive as is basically is expected to be. Then what is the solution? Because if you identify the challenges, at the same time, you being the technocrat, we need to also look at the solution aspect of that. Solution says that you have to ensure that there should be a multi-directional power flow, not only bi-directional. I would say that multi-directional power flow. So I will kind of try to explain each and everything related to it. And it should be communication-rich network, right? It should be resilient network. It should kind of have the strong resiliency involved into it, and there should be automated operation. It should not be manually controlled only. So if I say bidirectional or multidirectional power flow, that means there should be a provision with which the load can also feed power back to the source. Or not only that, load can feed power back to another load, right? And there should be a proper communication established between the all stakeholders, everybody involved into it, that okay, this is the surplus power that is available there. So you can extract that surplus power, can use it to some other location. So for those things, you need a very rich communication, rich network. And once you kind of set up all these things with you and connect everything with the network, you need to ensure the resiliency of it, right? And as I said that, then you need not to go for the manual operation. Everything will be automatically done. So solution at large is that in order to implement all these points, we have to ensure that there should be a distributed generation, and a lot of power electronics and control logic basically would be involved in order to optimize the source and load status, right? So there, as a power and controller, as a power engineer, we have got a lot of scope to work on to it, that okay, how can we ensure all these points with the help of the state of the art technologies that are available with us, and make the system basically a smart system that basically can, in which a load can talk to another load, source can talk to load, once load can talk to source, right? And you have got the dynamic information of all the points at a different time frame. So that is what the idea is. So eventually, if you look at the smart grid architecture, these are some of the basics. I'll try to give you some of the basics, and then I will also touch upon what basically we have done in our laboratory, as Samantha has described, that we are working with the National Science Foundation US, where University of West Virginia and Massachusetts, basically Institute of Technology, they are involved from their side, and IIT BHU, our lab, is involved from India side, and we have recently developed one smart grid architecture, smart grid model in our laboratory, and made it a cyber physical system connected. So that will come in the upcoming slides. But if you conceptualize the smart grid, as I said, that you can see that in this picture itself is a self-explanatory, where you can see that you have got the distributed energy resources, where you are other than your conventional resources, you can also generate energy with the help of these non-conventional energy resources, right? You have got the load that can feed power back to the grid as well. Not only grid as well, there is a load that can feed power to another load, right? So it can feed power to this load, or it can feed power to back to the building also. It can feed power to the home also, right? So that means you have a kind of multi-directional power flow with a strong communication network established into it, with non-conventional energy resources also playing their role as far as the building up of smart grid architecture or framework is there. So necessity is what? Necessity is that there should be a clean energy adoption. It should be sustainable, right? It should not be, the another aspect of this is that whatever you develop, that should have the self-sustainable, characteristic. Carbon neutrality is something that is going to be a big issue for not only for the India, for the entire world, right? And as I said, the distributed network, they are playing their role, because they replenish themselves. They are not dying down with the time. And for anything, there should be, up to certain extent, a self-healing capacity should also be there. So if you connect all dots together, you find that, okay, there should be a resilient system that supports sustainability, carbon neutrality, distributed network, clean energy, and everything, and self-healing operation. So having said that, so important aspect is that in the smart grid architecture, right, basically you have to kind of look into how the cyber physical system basically plays its role in building up of a smart grid architecture. So this basically slide gives us the information about the role of a cyber physical network for development of a smart and resilient grid architecture. So if you look at this diagram, eventually the things will basically be a bit clear about it, that if eventually what happens in the cyber physical integrated smart grid ecosystem, we used to have 3 different layers, right? The layer 1 basically belongs to physical layer, where all your equipments and interfaces and power electronic devices, they are playing their role. They do their operation. And layer 2 basically is the data acquisition layer, where you get information from the different devices that are playing their role in layer 1. And then layer 3 is the data analytics layer, where you do data modeling, data predicting. You come up with a model that do load prediction, dynamic modeling, demand response management, etc., and it again fed back to the basically. And this layer 3 is basically this basically generate reference, and that reference further goes to control the layer 1 again. So that's how loop basically gets completed. So layer 1, you have all the physical network connected. In layer 2, you are doing the sensing operation. Then layer 3, and again everything gets back to physical layer, because whatever is being calculated or being predicted in the layer 3, I mean, it is eventually coming back to the layer 1 in order to execute itself to meet out the requirement. So eventually, if you define what, why, how, you will find that there will be distributed energy resources, sensors, and IoT modules. And why it is required, we have already discussed about it, because you need to have more dynamic control on each and every aspect of the smart grid component, right? Not only dynamic aspect, you also need to ensure better reliability and secure the entire operation. And how can you do that? How you can do that, with the help of the power electronics basically plays a lot of role in building up of this cyber resilient or cyber physical system integrated smart grid ecosystem. So this basically slide gives us the information of how inverter based resources or the power electronics basically plays its role in building up of a smart grid ecosystem that basically is connected with the cyber physical network. So if you look at this particular diagram, you will observe that, okay, you can have your own generation from the distributed energy resources, then subsequently you feed it to the inverter, sense it, do the predictive modeling. As I said, that this may be the layer number 3, right? And this layer number 3 is kind of giving information to, again, the primary controller. So this layer 3 is giving reference to this controller. Now this controller will generate reference to control the inverter, and that's how entire loop basically gets completed up. So here, that is the kind of the elaborated version of this particular diagram. So here you can see you have got two different layers, physical layer and cyber layer, and in between there would be a data acquisition layer. So supposing you have got a battery, solar, and all those distributed energy resources with which you are generating power, then subsequently you are sensing it and trying to kind of come up with a modeling that will predict the demand response management, dynamic pricing, dynamic unit of generation at the input side, the load requirement, etc. And that's how you can entirely control the entire operation of a grid ecosystem, where you can say that, okay, if the generation is high, demand is less, you can accordingly take the decision and give an alert to the user. Or if the generation is less and demand is high, you can give an alert to the user that unnecessary loads may be shut down and everything. So that's how you can have the dynamic control on entire operation, right? So the objective is what? It will have the enhanced efficiency, reliability. It will be integrated with the renewable energy management, and demand response. As I said, that would definitely be there, and it will make the entire grid a resilient grid. And you will have a decision making with the help of the data that is available to you. And combining all these things together, you can also do the cost optimization, because it's not the linear operation, 0 or 1 operation. There are you are very, very smoothly managing each and every node dynamically, the load, the demand, the generation, the power utilization, and you can come up with a chart that out of 24 hours, in these many hours demand would be more, these many hour demand will be less. Accordingly, you can fix up the dynamic pricing as well and give the revenue or dividend to the customer who is basically utilizing less to that. And not only that, if you are integrating these energy resources, you are making the system cleaner also. So having said that, so this basically this particular slide eventually gives the further detail what I have already spoken of. So this is the physical layer, and from the physical layer, from the sensor and data acquisition system, you are feeding power to the cyber layer. And the cyber layer may have two operations. If there will be a stream data, or there will be a data that can be stored at the cloud. Now you can fetch the data from the cloud, or you can directly use the stream data. With the help of this cutting edge technology, artificial intelligence or machine learning, you do detection on and modeling, prediction, everything. You can also come up with the fault localization model. And as I said that, it will be acting as a secondary control loop that will generate as a reference for the primary control loop, and this primary control loop eventually will kind of monitor or run the power electronic interface that is sitting in the physical layer. So that's how everything right from the physical to the sensing unit to the cyber network, everything is well within the closed loop, right? So one is generating reference, and accordingly other is acting upon. And not only that, if you're connecting it to the cyber physical network, you will also have to look into the data anomaly, because your system becomes prone to the bad data. And when the system becomes prone to the bad data, you need to have that kind of technology available with you that will kind of detect that anomaly, and not only detect, it will also try to mitigate so that the healthy operation can be ensured all through. So with this background, I will tell you that this is the project that basically I was mentioning, that is being carried out with the help of these partners, Massachusetts Institute of Technology and West Virginia University. So they are our consortium partners from National Science Foundation US side, and IIT is the lead from India side. And in this, as I said that we have developed a smart grid and connected it with the cyber physical network, and we have also created a bad data into it, right? So in order to get to know that how resilient our system is, whether we are able to mitigate those anomalies or not, or etc., everything. So having said that, the physical or power electronics component, this part basically was developed here at our place. And the data anomaly algorithm has been developed by West Virginia, and its mitigation algorithm has been developed by Massachusetts Institute of Technology, MIT. And this particular test bed is fully functional at our place. And then up till now we have developed 3 kilowatt of model for this, and we have kind of implemented the data anomaly at different location. Like we have perturbed the generated power from solar PV, the voltage and the current, and then that perturbation went through our logic, and then our logic basically gets executed accordingly, and it kind of the outlier and other bad data basically were filtered out, and subsequently the real data basically went through, and it generated the reference for the primary control, and the primary control basically executed the power electronics component, and everything is working very well. So the role was that physical system, the physical layer was developed by us, right? The communication layer was developed by West Virginia, and the cyber layer was developed by the Massachusetts Institute of Technology. And recently I visited basically Boston, MIT, and I integrated our algorithm with the algorithm that they have developed, and the system is perfectly working fine. So if you have got any doubts so far, I don't know if you have got, I can see few hands raised. So Megha has raised her hand. So if you have got anything to clarify, I'll be happy to answer. All right, so no problem. So let's move on. So having said that, so now let's try to, I will try to let you know basically the architecture that we have built up with the help of one of our PhD students, right, as a part of that development. And in this, if you look at, eventually you will find that in the entire power electronic topology system or a network, the capacitor is something that basically used to be the weakest or vulnerable component amongst all. If you look at the devices or the filter, electromagnetic component, inductor, so you will find that the capacitor is someone that is very vulnerable, that is more prone to fault, right? And if you are, building up a two-stage system where you are generating power from solar PV, converting it by using DC to DC converter and feeding it to a DC link, and subsequently that DC link is kind of giving power to another interface, that is inverter, and that can be utilized for the grid system. Power can be fed to the grid, or it can be locally utilized. So in entire setup, this basically is the most vulnerable component. So we thought of taking up this one. So we, so the identification is what? Identification is that for building up of this DC grid, we use this heavy electrolytic capacitor, and this heavy electrolytic capacitor basically is more prone to failure, and that's how I can say that it has got very less life, and it has also got high ESR value, and reliability is very poor. So and if you compare the electrolytic capacitor with the film capacitor, you will find that the life of film capacitor is almost 3 to 4 times more than the electrolytic capacitor. Reliability is much better, maintenance cost is less, and there is no protection that is required for the film capacitor. So we thought of, can we come up with some topological modifications with which we can basically replace the electrolytic capacitor with the film capacitor. And this is what the capacitorless, we call it capacitorless topology, that we have developed. And here you can see that instead of using a heavy capacitor, we have used the film capacitor into it. And eventually what we did, we have modified the dual active bridge architecture, and we have come up with a new control algorithm with which the requirement of a heavy DC electrolytic capacitor, basically we could able to get away with that, and we could able to get the work done with the film capacitor itself. So we actually came up with a new kind of synchronous leg modulation technique, and that basically gave us improved reliability and better life performance for this DC grid architecture. So this is the complete this architecture or a setup or circuit diagram that basically has been implemented. The paper has already been published in IEEE transaction. So you may explore, you may go to my webpage, and if you want to have the further learning on this particular topology, you just go to IEEE Explore, get the paper downloaded, you will get all those information. But the important aspect that I want to highlight over here is that instead of using a complete DC signal here, we have generated a 6-pulse DC here, and that basically have basically helped us not only in reducing the size of the electrolytic capacitor, but also the size of the filter that is required at the grid side, right? And I will show you some of the, and these are some of the modulation techniques. I'm not going to, in the details of it. All these details are already there in the paper, so you can, refer to those papers and get the complete information about how this modulation technique work, basically what are the other advantages. But the important part that I want to highlight over here is, these are some of the results basically for 700 watt of model. So we simulated, we run it on the experimentation also. So just have a look at that. For the 700 watt, we could able to get the things done with only 5 microfarad film capacitor. This is highly, a lot of, improvement is there, because for this, if you need to create a DC architecture for electrolytic capacitor, you need a heavy electrolytic capacitor, almost 450, 480, 80 microfarad, electrolytic capacitor requirement is there. So just imagine, the value has gone down, significantly. Right. So with this very, less value of film capacitor, we could able to, achieve the desired operation. We also run the circuit on an experiment, and then, this particular basically, this result shows the output for 700 watt. Very recently, we could able to get the, desired result and operation up to 3 kilowatt of operation, and to the best of our, this expectation, the capacitor requirement hasn't gone up. Even for the 3 kilowatt of model, we could able to achieve the same result with the help of only 5 microfarad capacitor. So that means you need not to invest a lot for building up of a DC grid architecture by using electrolytic capacitors. That is a huge contribution. So then I will further try to let you know what basically we did with the help of those partners there, US partners. So as I said that the physical layer, then cyber layer, and then middle layer, basically we actually created all those layers, and these are the the description of those. So the physical layer has been created in OpenDSS. Then there is a cyber layer that has been created in the mininet, and the application layer has been created by using Python. And in order to wrap everything together, in order to, just join everything together, bind everything together, we use the Python wrapper. And, these are some of the results. So we connected everything with the cyber physical network, and we created, the data anomaly. And some of the usual data anomalies are man in the middle, denial of services, and replay operation. So these are some of the, data anomalies. They're very common data anomalies. So if you are, let's say, operating everything under the cyber physical network, so there will be someone, some unwanted third man, basically, who will come in between and, will try to disturb your smooth operation. So that is known as a middle of the man, middle in the man. Then denial of service. So it will, you automatically everything will shut down. You are nowhere. Or the same thing will keep repeating. Like so let's say there is a flicker in the supply. So there would be the flicker would be continuing. So those things we have identified, and we have identified these nodes 671, 684, 675, and 634 here. So we have created those data anomalies and identified, and finally we could able to, achieve that. Okay, the normal operation could be restored with the help of the development that had been done by the US partners, and we have implemented it on our setup, and we could able to find out that okay, everything is working well. So now that basically is there for the smart grid ecosystem. The second part is how about the role of an EV in cyber resilient smart grid ecosystem. So if you look at this entire architecture, so now as of now we have got the enough understanding that okay, smart grid architecture will have inverter based resources, it will have the distributed energy resources, it will have communication channel between the source and the load and the load. So it will be having a kind of multi-fold, multi-directional operation where lot of power electronics control is operation and communication operation is taking place. But if you consider electric vehicle in the present scenario, and you put everything in the perspective of what we are discussing upon, so you will observe that the EV basically acts as a load where you can actually charge it from the home outlet. You can do the fast charging or you can do the ultra fast charging. And not only that, it can also act as a source. So it can feed power back to the grid. It can feed power to the home. It can feed power to another EV, right? So it can act as a backup generator, and it can also act as a load smoothening, and it can also act as it can also act to kind of do the grid balancing, right? So electric vehicle has not remained only as a load. That's what my whole point is, that don't think electric vehicle as only as a load in the entire smart grid ecosystem. It will act as a load where it can supply power to the home, not only to the home, it can supply power to the building, it can supply power to another vehicle, it can supply power back to the grid, etc., etc. And it can also act as something that can smoothen the load, right? So if you have got these many operations basically to be performed by the electric vehicle, so what are the challenges? Challenges will definitely come in. So I mean, don't go, I'm not going to read all these texts, but this figure itself spells out everything. So the potential impact that this particular kind of electric vehicle charging that it is going to create is there would be an harmonics, there would be a flickering and interferences, there would be thermal stress, congestion, transformer overloading, there would be a voltage sag and swell, there may be a phase imbalance and a grid congestion. So eventually you need to kind of take care of all these issues and challenges that would be arising because of the impact that would be created because of the integration of a EV. And if EV penetration goes up the way government of India or the other federal government of different countries are expecting, you also have to be very careful, because whatever is coming from the utility grid, or whatever is going to another thing is going to through the utility grid. So your grid should be resilient enough, or you can say strong enough to withstand all these challenges associated with the EV. And we have kind of emulated everything in the laboratory. It's not that I'm only talking about in theoretical term. Whatever we say, we first do it in the laboratory, and then kind of try to convey the message to the rest of the world, right? So these are some of the potential issues that we also have identified, because in our research group, many of our students are working in the field of air, electric vehicle. We are handling few private projects. We are handling few government projects, consultancy. So there we have identified these issues. But okay, issues are there. So how about the solution? The solution says that, okay, there will be voltage unbalance. Right? So you need to mitigate it. You need to mitigate harmonics. You need to mitigate the voltage fluctuation. Because these three are the one that basically plays key role. The solution is that you need to come up with a state-of-the-art technology by using, let's say, artificial intelligence, data analytics. If you use all those state-of-the-art technologies, as I said, that cyber-resilient, inverter-based resources, then there is a solution, because you can do the predictive maintenance, you can do this intelligent demand response. Not only that, you can also do the optimum sizing of the battery. With the help of the these state-of-the-art technology, you can come up with a model that can predict the optimal sizing of the battery and dynamic energy management. It will enhance the grid stability and energy resource management. So, and that is where now I will try to connect my previous discussion with this one, that I said that, okay, there would be three layers in the entire smart grid ecosystem: physical layer, the middle layer, that would be communication layer, and the final would be the cyber layer, right? So with the cyber layer, where you are coming up with the predictive modeling by using data analytics and machine learning, deep learning, etc., you can perform all these tasks, and these tasks basically will help you out in doing the voltage mitigation, harmonic mitigation, and voltage fluctuation. So in a way, you will be comfortable with improving the EV penetration into the smart grid system. So what we do, as I said that, before we convincingly say anything, we used to do in the laboratory. Simant knows this, that, before I say that, okay, 5 ampere current is flowing, first we actually ensure that, okay, really 5 ampere current is flowing. Then we say that, yes, I'm convinced that 5 ampere current is flowing. So we also thought of, okay, let's try to, do something related to this role of AI for EV integration to the smart grid management. So in this entire smart grid ecosystem, as you see that, there is a electric vehicle here, and electric vehicle battery is very important part, right? Because you need to charge the battery, you need to discharge the battery. So the only element basically that you have to take care of is the charging, discharging of a battery. And how it will be done? It will be done through the battery management system, right? There would be a power electronic interface or train that will kind of ensure the charge profile, as well as it will ensure the discharge profile. So we thought of taking up of a battery and try to come up with a model that will predict the state of the charge, state of the health, and remaining useful life of a battery, right? Because ultimately that is what our goal is, that if we can come up with this model, predictive modeling, right, optimum sizing, energy management, so can we really do that? So that's the task basically we took up, and with the help of two of our brilliant students, one from the computer science engineering, so he's I'm co-supervising him, and with the help of another student who is working in the laboratory. So we actually started taking up this task of predicting SOC, SOH, and remaining useful life of a battery. So what we did, so that the computer science guy, basically student, he is very good in kind of this data analysis and other soft skill, soft aspect of the technology. So we calculated the real time. We actually took the real time data and injected the false data into it. Then did the pre-processing, data pre-processing. So data pre-processing meaning is the outliers will be kind of automatically be filtered up, right? So whatever extra data is there, that would be filtered up. So that this pre-processing part will do that. Then with the help of machine learning and deep learning algorithm, we are removing the false and outlier data and again feeding it to the pre-processing data, and if there is no false data or outlier, then it will go to the next model and it will kind of estimate the state of charge and state of health and remaining useful life of a battery. So with the help of machine learning and AI, we could able to do that. So these are some of the parameters. So if you look at the battery parameters are what? Voltage, current, temperature, right? Then the circuit data, there would be seasonal data, there would be, the throttle and speed data. So, in the battery, a lot of things are there, because battery may behave differently in a extreme summer and it may behave differently in a extreme winter. So we did the, we took the data from the winter, from the summer. We took the temperature data and tried to come up with a model. This is the flow basically with which we could able to do that. So as I said that we took, collected, millions and millions of data, did the data processing, feature selection, model selection, and then finally performance evaluation. So I will not actually go into the further details of it because this is, something that requires, bit of a time to further explain each and every component of it. But at a high level, the whole idea is that you need to pre-process, then do the feature selection, model selection, and finally come up with the state of the child model. So this is what the result basically that I want to, show it to everyone, that we actually took 72 real driving trips with a BMW, took the data, and with the help of the thing basically that I have explained in the previous 2 slides, we identified, injected the false data, mitigated that, rejected the outlier, and finally, if you look at, the predicted state of the charge is almost following the exact state of the charge, right? Almost following. So that means this gives us a confidence that, okay, whatever model you have developed is really working, is really, justifying the algorithm, is really doing the justice, right? So, and we did, as I said, that there were 2 categories of data. One was in extreme summer and another was in extreme winter, because in Western countries, basically in some winter season goes up to -45, -50 degrees C, sometime. And in our country also, even in the city of Varanasi, we are facing 8 degrees, 4 degree, 5 degrees sometimes. And in extreme winter, extreme summer, you will have the temperature up to 48, 49, 50 degrees, right? So you need to kind of comprehensively analyze all these things, collectively, and then do your predictive modeling. So eventually, this is the method. Those who know a bit of a computer science, they might be knowing that GRU and MSDTCN basically is the model that we have selected for our case. And if you look at, almost in every, parameter metric, the proposed, system is kind of performing better in comparison with the existing solutions, right? So I will share this slide with the Simant, and he can further transmit it to you for your further information. Some of the details are still under publication, so those details I cannot share. But yeah, whatever I can share, we'll definitely do it with the organizers. Another very important topic or a concept is, cyber physical network in electric vehicle, right? Need of a communication, and that becomes very important. So this particular cycle basically will explain you everything. So if you look at this cycle, you will find that there is a communication between vehicle to charger. Then there is a communication between charger to the network. Then there is a communication between network to network, then network to charger, and then charger to vehicle again. So this loop gets completed. Why this is important? So let's say I'm a EV owner, and I have booked my, book to get my EV charged at a particular charging station. But when I reach out to that place, I find that a lot of rush is there, and I have to wait for 45 minutes, 1 hour. So with the same booking, whatever, if I have made my booking to this charging station, if everything is communication rich and connected with the cyber physical network, right, I can transfer my same booking to this charging station and move out to this charging station, and if I find that, okay, the rush is less, with the same payment and everything, I can get my vehicle charged at this particular charging station, even if I have booked my charging for this particular charging station. So for those things, you need a strong connectivity between the EVSE to vehicle to network to this network to and back. And that's how the flow of data basically plays its role and plays a kind of, the cyber physical system basically plays its role in entire electric mobility architecture. And of course, CAN is the one, is something that basically is there. So there are some protocols, right? So this protocol, so EVSE communication produces a very standard and very popular ISO 15118. So this basically is used for road vehicle to grid communication. And there is another protocol that is known as Open Charge Point Protocol. So it enables communication between EVSE to host network, right? So similarly, we have got, and CAN, because it kinds of, it is a protocol that basically gives display to your dashboard, right? What is happening, what would be the state of the charge, remaining useful life, state of the health. So through CAN, network, you can get all those information. So, right. So if you look at at least this particular diagram, you'll find that if you are a EV user, this is a service provider. So there should be a bi-directional communication. And not only that, the service provider is communicating to the charging station, and charging station can communicate to back to the EV user. And not only that, the grid can communicate to the charging station, and the service provider can communicate to the back and forth to the grid. Means he can establish the bi-directional communication. So the role of a communication becomes very important in the smart grid or smart e-mobility ecosystem, right? By now, I think things should be clear to you. This slide is very close to me. I always, whenever I get a chance to speak something on e-mobility, I don't miss out to, put up this slide before the audience. So if you look at this diagram, you will observe that each and every component has got a protocol. Even onboard equipment is identified by some number. EMC is identified with some another number. And, then connection is identified with each and every, component of a electric vehicle is identified with some standard and protocol. And this standard and protocol basically defines the identity of a device. So if you are not actually following these protocols, there should be a system that should not allow your vehicle to charge, because it is not as similar as charging your mobile phone, because you don't need any protocol into it. You just plug the charger, put it with the utility grid, your battery will get started, battery charging will get started. But in this case, unless you are having the exact protocols following with each and every component, even if you plug your vehicle with this charging station, it will refuse to accept your vehicle at all. And that is what the role of a protocol, role of a standard and communication basically is in the entire system building up. So yeah, that is all. And I may skip this, but as a custodian of my research group, this is what the information of some of the information related to my research group. Simant knows it very well. He is our student. So we are presently handling 6 projects. 7 have already been completed, more than 7.6 CR. Basically, we are managing, and these are the funding agencies with whom we are working. So good part is that we are also, engaging ourselves not only with the government organizations, we are also engaging ourselves with the private industries and international players as well, right? And if you want to further get some information about the profile of the lab or my profile, this is the URL. You can go through that page and get the information. In the introduction, Simanta has already mentioned, although of course this number has gone up. This was some previous numbers. So this is the group information, and if any one of you is really interested to do something in power electronics or something related to smart grid or electric vehicle, you are welcome to join our research group. right? And we are extensively working in the area of e-mobility. And the whole idea is that we are not only trying to confine ourselves within the boundary of the laboratory. Our whole target is that, how can we come out of the boundary and then really do develop something that can be implemented on a real-time system. And I'm happy to inform that, one of our development is going to be implemented by Tata Motors Limited very soon. So we are developing a low-cost onboard charger, where we are reducing the cost of a charger by more than 50%, and that the commercialization journey of that particular development has already been started. And if everything goes well, in times to come, Tata Motors will take up that. Or there are some other companies, right, who have shown interest to take up that technology and do the commercialization of that. So with this, I will end up with some points of discussion. And these are very important for your contemplation, right? So smart grid ecosystem, it is needed, it is contemporary, and it is futuristic solution, right? So you just try to think on it. If you want to do something related to power electronics, these are some of the things that you can try on. And integration of inverter-rich resources for cyber physical architecture, EVs and cyber physical network, right? So how can you eventually improve the cyber physical performance? How can EV and cyber physical network basically have got relevance with respect to each other? And not only that, protocols and standards are there, and they are very crucial for making an impact as far as the EV integration into the smart grid is there. So with this, thank you very much, and I would really be happy to take up the questions.
Thank you, sir. Dear participants, is there any questions you can ask through chat, or you can unmute your mic also?
Professor, good evening, Professor. I'm Narayanamurthy, from faculty from SRM University, Chennai, and thank you for very inspiring presentations. I'm following you for last few years, and I just want to know the usage of or the future of wireless charger towards Indian market. So how we can?
It's a good question, Narayan Murthy. So see, wireless charger, definitely they have a lot of potential to be accepted. But if you look at the Indian scenario, we are actually far behind from where Western countries are. So we are still looking to catch them up, right? So that is why whenever you talk about the wireless charging system, dynamic or static, right? So people have apprehensions here in our country. But just to let you know, recently, there was a conclave in IIT Delhi in which Ministry of Road Transport and Highways, they were also participated, and they are contemplating to identify one national highway from Delhi to Jaipur, and they are identifying that national highway as a e-highway, right? And certain patch of that e-highway, they are thinking to build up to charge the vehicle dynamically and wirelessly. So you just move your vehicle on that particular lane, and for let's say for 30, 40, 50 kilometers, and your vehicle will get charged by 50%. But still, whenever I get a chance to talk to these, policymakers or technocrats, usually they say that, okay, first let us set up the wired system, comprehensively in the country, and then move on to the wireless system. Though in our laboratory also, with the help of one of our students, right, he is the faculty member at NIT Calicut now, we have actually developed a small model of 500 watt where we have transferred power wirelessly up to 12 centimeter by using some state-of-the-art power electronic interface. So from the Indian perspective, people have apprehensions, but yes, wireless charging definitely is well accepted, in the Western countries.
Thank you, Professor.
Sir, I am Dr. Vivek from BRCM College of Engineering. Good evening, sir. My question is that how long it will take your prototype charger will come into market, sir, in Indian view?
I mean, yeah, I'm also trying to push it hard and trying to have it as soon as possible. So actually, there is a different journey altogether. So we as a professor, we also didn't know before that up to verifying something in the laboratory environment and doing the proof of concept is one part of journey, and there is another very big journey that basically is there after that. When you have done the proof of concept in the laboratory, you have done everything in the laboratory environment, and then now if you start your commercialization journey, lot many things basically come in, because you need to do the certification, you need to get the field trial, road testing, this, that, everything. So at least we are almost halfway through. So 1.5 kilowatt model have already, that model has already been tested and field trial has already been completed here, right? And now we are at the stage of developing or testing it, that 1.5 kilowatt model for three-wheeler e-rickshaw. So we have already tested that, and we will put it up for field trial in next couple of months. That's what our plan is. So probably in next 1 quarter or 2 quarter, the things should come in the market. That's what our expectations are.
Okay, thank you, sir.
Yeah, I think there is a question on the chat box. So what role do predictive analysis play in identifying potential vulnerabilities? Yes, so predictive analysis, as I mentioned in one of the slides, that this predictive analysis basically set as a reference for the primary controller. So if your predictive analysis part, that basically comes under the secondary controller. So if secondary controller is working proper, then it will generate the proper reference for the primary controller. So if the referencing is done for the primary controller, proper referencing is done for the primary controller, then accordingly your physical layer will execute in a fashion in which we are expecting it to do, right? So in that way, the vulnerability basically can be well within control if you are designing your predictive or analyzing your system or generating your secondary, designing the secondary control properly. So it has got a role. PN Raj Narayanan. Yeah.
So, any other question, dear participants? Hello.
Yeah, you may connect me offline also, through organizers or through Simanta. So if you have got any further query or apprehension at some later time also, just you can reach out to me or my research group. So we'll be happy to, again connect back to you.
Thank you, sir. Thank you for your this lecture. So we are expecting in future also very soon. With this, we are concluding this session. So next session will start shortly. Thank you, sir.
Thank you. And I will request both of you, Dr. Mrinal and Simant, if you can, share the feedback, because I also need feedback for my improvement.
Yes, okay, sir. Okay, definitely.
Yes. All right. All right. Okay. Thank you. Thank you very much. Namaste.
So, dear participants, our next lecture will start shortly at 7:30 sharply. Please be with us.